So finally, we're covering the Schrodinger equation for this video. So the kind of basic idea of the Schrodinger equation is using the law of conservation of energy to, well, motivate it. So if we take it that the energy in a closed system is always conserved, no matter what, then we could kind of intuit that this Hamiltonian operator, I'll get into what that means in a second, acting on the wave function is the same as just the energy multiplied by that original function. So what does this Hamiltonian operator mean? Well, it's essentially the sum of all the energies that you have. So if you had something like the kinetic energy and the potential energy, well, that would just be your Hamiltonian operator. So this is what that would mean. So if you take the sum of all energies, energy operators, and you make them act on the wave function, well, then that would mean the wave function would have to be an eigenstate of that operator because the energy is conserved. If it has some kind of energy, then it should be conserved. That's kind of the basic idea of this whole thing. And this is actually kind of it for the time-independent Schrodinger equation. So this does not have time dependence taken into account, which is why we will derive the time-dependent Schrodinger equation in a second. But this is kind of it. You can still use this for a lot of cases, like stationary cases, where the energy doesn't change. But now let's think about what happens when the energy does change. And to figure that out, we will need de Broglie's hypothesis again, but we will use it a little bit differently this time. So instead of differentiating with respect to space, I have differentiated with respect to time this time. So what we will end up with is just this negative I times omega, right? Negative I times the frequency. If we use Planck's equation, which is that E equals h bar omega, right? Then we can rewrite this equation like this, where I've added this kind of time dependence on energy. Because again, we're thinking about changing energies. And in a sense, we're kind of almost pretty much done. All that we need to do is make this independent of coordinates, because notice that this space wave function is in the space basis. So we have to figure out how to make this independent of basis. And to do that, it's actually not that hard. All we have to do is use some clever trickery. So here I have rewritten this half of the equation in terms of our position, in terms of the kind of independent of basis representation. And here I've utilized the identity operator, but I've used a different set of coordinates because I've already used x, so I'm using x prime here. But what this tells us is that we need this little part to have this delta function in here, because we need to be able to transform from the x prime basis to the x basis, because they have to be the same. So everything that's in here has to essentially be a delta function. And as it turns out, delta of x minus x prime is just the dual of x acting on x prime. So from here, we can just read off that E must be IH bar times d by dt, which is actually what we had up here, but it's nice to kind of make sure we were right with this kind of rigorous approach. So now that we have this energy operator, we can replace it with this, and since it's equal to energy times psi, and we also had the same thing over here, we can arrive at the time-dependent Schrodinger equation, and it's also independent of coordinates. So this is kind of the most general form of the Schrodinger equation. It works for any basis, it works for any kind of situation. It's kind of the most general. So anyway, I think that's kind of a good place to end this series, the short series. So yeah, thank you for watching.